So let us, I'm going to uh, talk about very briefly about the sessions. In these sessions, we are having representation from HPCL, EIL, Geometry, and Reliance Industries Limited. And the esteemed speakers are going to talk about specific and interesting topic and the innovation they are doing in manufacturing. With that, I'm going to invite our first speaker, Mr. Akhilesh Tiwari, to come here. My colleague and I together is going to talk about a specific topic that Reliance developed for improving the manufacturing efficiency. As we know, for decades, our manufacturing industry and energy industry is defined by great innovation and constant pursuit for efficiency improvement. We are continuously doing it with the help of fundamental models. However, that has some limitations. In last decade onwards, with the improvement of computational facilities and artificial intelligence, working on huge amount of data that is being generated by our manufacturing shop floor, we are using those data and creating the solution that was never possible with our fundamental models. And application of this requires a lot of collaboration among different functions, the domain, the mathematics, the computational infrastructure, and the AI algorithm. Without collaboration, no solution is going to provide the intended results. The solution today we are going to talk about is such a solution where there is a collaboration from multiple functions. If we see in one of our survey, recently we found that around 70% of the data that manufacturing industry are generating are being collected and historized. Out of that, only 46% of those data are being utilized for developing insights and improvement of the operations. And with that, having huge amount of data not being collected, and once data being collected not being used, from the last few years onwards, the AI having the algorithms available with improved computational facilities, we are using those data and creating operational insights to improve the efficiency. If we see in our manufacturing, the data are residing at different locations, different systems. Those data are being captured, translated, AI is being applied on it, and creating multiple path-breaking solution that we would never imagine that we could have been done with our fundamental physics-based model. With that, today I will invite my colleague to talk about one of the solutions that has been deployed in Reliance using the data, and specifically would like to mention that these solutions are not only talking about what we are doing now, these are forecasting what is going to happen in near future. The solution that is going to be talked by my colleague now could predict some failure around 5 months earlier that it happened, such that action could have been taken to avoid it. With that, I will invite my colleague Akalesh to talk about the solution.
Thank you, NC. I hope I am audible. Yeah. So basically, the solution that we are presenting today is for a platforming unit. It's a refinery downstream unit, and the typical setup of a plant that comprises of the platforming technology is shown here on this slide. So the focus area is platformer. This is basically converting the straight run naphtha to aromatic rich feed, which is further processed to produce high purity aromatics like benzene, toluene and xylene, and it also produces hydrogen. So the focus of the solution is a platformer. So in this platformer, one of the key units is catalytic, continuous catalytic reformer and the regenerator. So basically, as the reactions actually happen in reformer, the catalyst gets deactivated, coke gets built up on the surface of the catalyst, and this catalyst needs to be regenerated before it can be used again in the reactor. So this regeneration happens in the regenerator. The regenerator basically regenerates the catalyst by burning the coke that gets formed in the reactor. So the focus area of our solution is this regenerator. Even in regenerator, there are multiple sections, like there's burn zone, there's reheat zone, chlorination zone, drying zone, and cooling zone. We are focusing on the burn zone. Now in this, the top section that you're seeing in this drawing is the burn zone. And in this burn zone, there are multiple temperature sensors are provided so that the temperature profile across the length as well as the radius of the column can be tracked and can be monitored. Now, as the catalyst leaves the reactor, it comes to a hopper, and then from hopper, it passes through the burn area of the regenerator. Now, these on the rightmost plot, you see some dotted lines actually. These dotted lines, these are nothing but the screen, the outer screen and the inner screen. And the area that is formed by this, both these screens, the catalyst actually flows through that area, the annular space between the outer screen and the inner screen. And it is here the catalyst is brought in contact with air, the combustion reactions happen, coke is burned, and the products of the combustion that they leave to the center of the column, and then it leaves, goes to the blower. From blower, it again comes back to the burn zone. So the dotted lines, the inner screen, that actually often there's a possibility that it can get choked, and once it gets clogged, then it can cause a reliability issue. Eventually, it can lead to the load reduction as well as it can lead to unplanned shutdown. So, identifying the onset of this blockage actually is of paramount importance, And that's what this solution actually is doing. So there are some conventional means by which the condition of the inner screen can be identified, can be inferred, and these are the temperature profile, the top regeneration gas flow, and the oxygen concentration and catalyst circulation rate. Now, out of these parameters, the regeneration gas flow is one of the lagging indicators. There's no control on it, but once the flow gets, as there's plugging in the screen, the flow reduces, and about 10% drop in this flow indicates that there's 30% clogging in the screen, and eventually the plant needs to be shut down for the repair once this happens. So this is one of the lagging indicators, but it does provide some inference on the screen condition. Apart from that, the temperature profile is also one of the good indications, but this temperature profile needs to be assessed, evaluated in conjunction with the oxygen concentration that is there in the burn zone, because it's a function of coke to air ratio. And it also depends on the catalyst circulation rate. So whenever if the catalyst circulation rate is high, then it can actually shift the temperature profile. So on the plot that has been shown in this slide, that's how the typical temperature profile looks like across the burn zone. So the maximum peak is usually maintained in the top half of the burn zone. And for that, the oxygen concentration is adjusted. So eventually, to draw the inference on the screen condition, all these parameters are required to be looked together and analyzed. Then one can actually identify what is the condition of the screen. And because of the interdependency of these parameters, often the onset of the screen plugging gets delayed, and then it leads to further process issues. So this solution actually addresses the challenges associated with this conventional means of monitoring the screen condition. So the solution that has been developed, it comprises of multiple models, and all these models can be broadly classified into two. One that supports the conventional monitoring means, where it utilizes the historical data. We'll see there are three elements in this section. We'll see those in subsequent slides. And the second category is where we have made use of pure ML AI-based solution, which actually predicts the screen plugging event. That's the model development process at a glance. We've collected the data more than a year. We've cleaned it. Then the variable selection, most of the variables which are around in and around the regenerator burn zone, they have been selected. The data has been labeled so that it can be used in the model development. Then we've made different models, and these models, out of these models, we have selected the best model. So like we've developed three models: principal component analysis, Mahalanobis-based model, an autoencoder decoder model. Out of these, we selected the principal component model because it is simple as well as it was more reliable and more accurate. So we also have the ML-based multivariate early event detection model. So here also we built two models. One is the logistic regression-based linear model, and we also made use of non-linear technique, support vector classification model. Out of these two models, we found that the logistic regression model was giving better result, and since it is simple, we decided that we'll go ahead with it. So apart from this, then came the model deployment and then the UI UX development. In the UI UX development, we have the results published for both the categories of the models, one which is supporting the conventional mean, and the other one which is making use of data-driven AI ML-based models. Talking about the solution that complements the conventional means. Now here, the solution basically focuses on tracking all the temperature profile across the height of the regenerator. Now these plots that you can see is there are temperature profiles shown here, and there's a dotted line that you can see. That dotted line actually is a reference temperature profile, because earlier we saw that this temperature profile, it strongly depends upon the coke by air demand, it also depends on the catalyst circulation rate, and it also depends on the oxygen concentration. So for given coke by air demand, catalyst circulation rate, and oxygen concentration, the model goes, looks into the past data and finds out the reference temperature profile, and that gets shown here, so that it is easier to compare whether the current operation is as good as the past operation or not. If there is any deviation happen, it is easier to identify through this. So this is how it is actually supporting the earlier conventional mean of tracking the temperature profile. The other lagging parameter that we saw is the regenerator top gas flow. So here, to track the regenerator top gas flow, we made use of univariate SPC, and you can see on the left-hand side the cumulative Q-sum chart for the regeneration gas flow is shown. So the same signal you can see gets amplified when we make use of Q-sum plot, and it is easier to identify the drop in this the regeneration gas flow. It helps in identifying the thing. Talking about the ML AI-based solution, here, as I said, we've developed two models. The process deviation identifier, basically, it is a multivariate early event detection model, and it has been trained using the normal process data. So it identifies whether the current process is normal or not, and if the current process is not conforming to the normal operation, then it tells us which are the variables which are strongly correlated to the abnormality, so that the user can actually drill down and identify the root cause of it. The screen plugging detection model, again, this model, this being a logistic regression model, it tells us whether the screen plugging has started or not, and if screen plugging has started, how the model has reached to the conclusion that also actually it provides. So we deployed this solution in two sites in RIL Jamnagar facility, and it could actually detect the screen failure 5 months ahead of the actual failure. That provided us the enough lead time for planning the shutdown, and it also provided sufficient time to procure the replacement material. This is the deployment architecture. The solution, the architecture has near real-time data extraction. It has the environment where model can be executed, and the results can be generated and saved in the storage, and then the results can be published on the user interface. So that's the deployment architecture. We'll quickly go through the validation screen failure. This is how the model output looked like. Even the CCR screen failure, the logistic regression, we can see it was giving a good result. And when the column was inspected, we found that there was screen breaches in 2 locations, and multiple locations had screen plugging. So before I wind up my presentation, I would like to acknowledge the expertise of our domain experts who continuously provided us support during the project, Mr. Jasim Ali, Mr. Vasant Warke, Mr. Sachin Matre, and Mr. Paras Pawar. They all domain knowledge help us developing this solution, conceptualizing this solution, and it was very critical in the success of this project. So with this, I'll end my presentation. Thank you so much for patiently listening to me. Thanks a lot.
Thanks, Akalesh. Now, I invite Mr. Francisco to speak on his topic on adaptive promoting.
Thank you, Mr. Chandrabati, to introduce me. I'm very thrilled to be here with you to talk to you about one of the latest activity that we carried out in the robotics team of the innovation department of Baker Hughes. This topic is about an adaptive robotic approach for debarring workpieces with high geometric tolerances. And I want to start by stating something trivial, something obvious that you all know. When a person is performing a manual operation, they are capable to perceive the environment, to react to what they see, to what they feel. And we can say that this activity is a closed loop system in which the person reacts constantly from the feedback he receives from the environment. Oops, sorry about that. On the other hand, a robotic operation, as you know, is usually safer, quicker, and repeatable. The robot is doing the same thing no matter how tired he is, or no matter how bored he is, but usually he cannot perceive the environment, he cannot react to what happens. So the robotic operation is usually an open loop system. We want to make sure that all the repetitive activities with low added values are automatized as much as possible. But a repetitive activity is not always repeatable. If you have variability in what you're doing, you cannot approach with a standard robotic open loop operation. And that's why you have to create an automation of a complex and variable task by introducing perception to robots, to make them aware of what they're doing, to be able to perceive the environment, and to be able to actually react. And you can do that by introducing sensors, by introducing modules, self-programming modules to make the robot capable of programming itself, a object recognition module, a correction module that can correct the program according to the sensor that the robot has used, and also a quality control module that can allow the robot to check for its own work and to qualify its own work, or maybe to repair and correct it. But why is debarring, so the removal of bars from a component, a challenging process? For two main reasons. The first one is related to process input. So if you have a geometric variability on the component, if you have relatively high tolerances, the actual position of the edge you want to debar might not be always the same. So a standard approach, an open-loop approach, does not fit in this case. Then you may have variability also in the bar quantity. You may have a very little bar to be removed or a very high bar, and you cannot approach the debarring process in the same way. The second reason why the debarring process can be challenged is the requirement of the output. You may do not want to accept any residual bar, but you may also want to have a very little chamfer on the component. And that's why you cannot have a complete debarring sometimes with an open loop system. So in order to achieve a complete automation of the process, we created in our robotics lab in Massa in Italy a system composed by a robot on which we installed a spindle. It was a sensorized spindle, but we didn't use the sensors in the control loop. We just used it for a better understanding of the process in the early stage. And we integrated the actual protagonist, let's say, the actual sensor that allowed the perception of the environment by the robot, which is a 2D laser scanner, also called as profilometer. How does it work? A profilometer is basically a device that projects a laser beam on a component and is able to retrieve the profile coming from the intersection of the laser beam to the component itself. So here you see how the robot is going through a component and scanning it and acquire a lot of profiles. From these profiles, we can retrieve two main informations, the ones that I've talked before that are highly variable. First, we can localize the edge, and secondly, we can quantify the bar. To localize the edge, we basically take the profile, we take the topmost point of the profile, and we divide it into areas, the left-hand side and the right-hand side. For those two areas, we approximate with a straight line, and we consider the edge point, the actual edge point, which is different from the nominal one, as I said, as the intersection of these two lines. Then, once we have this information, we can use that to quantify the bar. So we take our edge point, we take our lines, and we state that all the points that are above the lines in a certain area close to the edge point are basically birds. So with this information, we can analyze from a geometrical standpoint this bar and understand its height, its width, and the integral beneath them, its area. Okay, so what is the barring workflow then? First, we scan the component. We send the robot to scan the edge that we want to debar. So we go with the laser scanner and pass through the whole edge, and we trigger the laser at a very high frequency, retrieving the two information I just said for all the profiles we get. So we get the nominal edge localization composed by all the edge points that we found on the profiles, and we can quantify the bar. Okay, then the robot is capable to create its own program then. How does it do that? It starts with first debarring pass, which is a translation of the edge that is found by a quantity that is depending on the maximum bar height that he has found during the previous scan. Then he performs a sequence of passes, getting closer and closer to the component, up to arriving at a slightly inside the component itself, in order to make a tiny chamfer and make sure that all the bar is taken away. At the end, the robot goes and scans again the component to see if it did properly, and if this is not the case, if some bar has remained, it starts over, basically, and performs again the sequential passes that I have just described. So here you can see basically how it works. The robot goes and scans the profile it needs to the bar, and then calculates instantly its own program and starts and does that. During the scanning phase, it's saying to the laser scanner its own position, and the scanner is answering with the actual position of the edge. Okay. So these are basically the components that they want to debar, and we saw that even with low bars, we achieved complete debarring, both with low bars and with high bars. You can see at the right-hand side of this component, we have a very thick bar, and we completely remove that, leaving a very tiny chamfer. All this has been done without any information regarding the CAD of the component. We tried to do that to make it tougher to be done, and we achieved very good results. And this allowed us to start the industrialization and take it into production to have a complete automation of the system. So just to wrap up, in our laboratory in Italy, in Massa and Florence, and the robotics team of the innovation department of Baker Hughes, we developed an intelligent robotic solution for the barring to tackle this low added value activity and to fully automatize that. We did that to increase the quality and reduce the rework of the manual debar needed, and to decrease the operation cycle time. So, if you have any questions regarding this activity or the others one carried out by the robotics team of Baker Hughes, feel free to reach me out at the end of the presentation at the back of the hall. So thanks a lot, and I'll pass the ball to the next speaker. Thanks.
Thanks, Francisco, for sharing such a high precision robotic solution that improves the quality and reduce the recycle. So next, I'll invite Mr. Vinod Kumar from Hindustan Petroleum Corporation for talking about material, higher performance material for 3D printing. Mr. Vinod Kumar.
I'm hope I'm audible. Yeah. Good morning, everyone. First of all, I would like thanks to chair, and I would like thanks to IEW and HPC for this opportunity. So, just I will give some short intro what we are doing and who we are. So, Hindustan Petroleum is like 50 years old company in oil and gas sector, and it's having two refinery in Mumbai and Vizag, and we based on R&D Bangalore, situated in Bangalore. This HPCL R&D center is started in 2012, and it started full function from 2017. So our core purpose of our R&D is to make energy and chemical accessible to everyone through innovation. So from our R&D, we have filed 628 patents, and 236 are granted. Out of 236, 61 products and technology we have commercialized, and this is one of the product out of that 61 what we commercialized. So this product is based. This is advanced polypropylene homopolymer composition for 3D printing applications like additive manufacturing. So if you are seeing like 10 years before, additive manufacturing is like a process of like prototype process, but there are multiple like recent growths. It's make it like a production method now. So there are different 3D printing methods are there, like starting from filament based and powder based, then liquid resin based. So what we have developed this polypropylene composition for filament based 3D printing applications. So from in case of this filament based 3D printing applications, there are multiple materials are available in commercial like polylactic acid and ABS base. So in case of polylactic acid and ABS base, these are all like imported material, and we can't use this polylactic acid for industrial application like final functional application, end use applications, and ABS is like in case of 3D printing, that ABS suitability is very less. It will lead lot of issues while doing 3D printing. So we took an objective of to produce 3D printable like material from polypropylene homopolymer, which is in like completely indigenous and low cost material compared to commercial materials. So there are requirement we observed from different 3D printing forums while we visiting for commercial trials and all. So we observed the who are all having 3D printing, they need material to resist chemicals and this heat and fatigue, and they need high strength material compared to conventional materials. So if you are seeing this high heat resistance and high chemical resistance, polyolefin is one of the like best material for these kind of applications. But issue with polyolefin, we can't print percent polypropylene or polyethylene in 3D printing. It will create again lot of issues while doing 3D printing. So we have modified this polypropylene to make it is a 3D printable by our indigenous additive compositions. So whatever we produce, it's like completely 100% indigenization, and it's very cost effective, and It is having like improved mechanical and thermal properties compared to conventional commercial whatever 3D materials available in market. So if you are seeing this global demand of 3D materials, it's in 2025 it's around 1.05 billion USD market worth is there, and it will grow like 2.58 billion market by 2030. So these are like imported like foreign major players like Stratasys, Sabic and Evonik. So if you see Indian market itself, the current requirement is around 4,600 metric ton, and it can grow up to 36,000 metric ton in 2020. So how we achieved this 3D like 3D printable polypropylene we call HP 3D PP. How our journey is from concept to reality. So first we started lab research. We prepared almost over 100 plus composition. From 100 plus composition, we finalized 3 final composition for this 3D printing application, and we have evaluated at lab scale in commercial like industrial 3D printers. Then we went scale up like 200 to 500 kg scale up, and we have supplied all over India 3D forums to evaluate our material. Then we started to selling our material in from March 2024 under through our HPCL marketing Petrochem marketing team under brand name of this HP Durafol S3D170. So if you are seeing title, we have developed this 3D printable polypropylene from polypropylene homopolymer. So why we choose like homopolymer PP? So if in India, if you are seeing who are all having this petchem, almost more than 80% is polypropylene homopolymer based, and only 20 to 30% this random copolymer base will be available. And this random commercial this manufacturer are having random copolymer base, but there are some issues like 3D printing this who are all having 3D printing, they are facing some issues with this random copolymer polypropylene based filaments. So these are the challenges they are facing. There will be like 2 mechanical gear to feed this material into this 3D printing nozzles. So due to this mechanical force, this random copolymer filaments is getting damaged due to its more flexible in nature. And also, if we are going to print pristine polypropylene, so we are going to face this warpage issue due to poor interlayer adhesion and poor interlayer adhesion. So these are the challenges in polypropylene. First one is feeding issues. Then higher due to higher crystallinity, that warpage is going to happen. Then shrinkage issue always it will be there. Then this poor interlayer adhesion will be there. Then if we are going to print any like complex shape, then we have to give support while doing 3D printing. So if you are going to print with pristine PP, that support removal also is like major task, and it will affect geometrical accuracy. We can't use in functional end use parts. So these are all challenges we addressed while developing this HP 3D PP. First one is like imported dependency on this polypropylene homopolymer based filaments. So due to monopoly, this polypropylene, this copolymer based filaments market cost is around 12 to 13K per kg. And even though if you are ready to pay that much of amount, that delivery time is more than 3 months, so we will not get material that much easy. So we given a solution like we have developed this HP 3D PP to eliminate this import dependency. Then cost wise also it's like huge, and we have like very cost competitive. We are supplying in very low cost in market. And the major thing is end use applications. So whatever material currently it's available, only we can use for prototypes or we can use for demo aesthetic applications. But in with our material we can go for end use like functional end parts also. Out of that, mainly we focus on this medical prosthetic socket for amputated leg. So it's current whatever commercial current material is available, it's like heavy in weight and expensive also, like normal patients can't offer this kind of high cost material, so we given a solution like low cost material with we reduce the weight also. So if you are seeing this commercial material and our material, this property comparison, we able to achieve almost threefold property in case of mechanical and thermal, and we maintain similar flow property compared to commercial material for easy processability. So how we have achieved this
Good morning,
HP3D-PP?
ladies and gentlemen. We welcomes you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 5 p.m. All visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the halls. Please take care of your belongings. Thank you.
Sorry. So how we have achieved? We have developed our indigenous like in-house novel additive package. So if you are going to add that additive package in any polypropylene grade, it will be like 3D printable. This additive package will help to improve this interlayer adhesion, and it will reduce the warpage and shrinkage during 3D printing. So this is what earlier I mentioned. Whatever current material people are using for this amputated prosthetic socket is polyamide base, and imported material cost is around 8,000 per kg. And that weight of socket what we have printed with polyamide, it will be around 230 gram, and it can withstand up to 120 kgs weight, like patient weight. But what we have developed material like HP3DPP polypropylene base, this highly cost competitive. We can consider like 1/10 of cost, and whatever prosthetic socket we printed with our material is like almost 80 gram lesser than that commercial material, which will help for patient for easy walking and all. And our material can withstand up to 153 kg patient weight. So apart from medical prosthetic, there are multiple applications we can use our material like equipment, spares, automotive, and rigid packaging application also is suitable. Then we have started this material for commercial selling under this HP Durapal H3D170. This is our patented product, and we started selling in market from April 2024. So in case of overall conclusion, like our material, we can modify our material properties depends on end use applications, as well as like it's suitable for all the 3D printing like FDM based 3D printer, whatever is available in market, and it's completely 100% recyclable compared to these commercial materials. Thank you.
Thanks, Mr. Vinod Kumar, for exchanging the knowledge of 3D printing raw material, which is one of the pillar of Industry 4 technology for manufacturing or sustainable manufacturing, not only for the application in medicals. This has a lot of other applications in our manufacturing lightweight materials. Thanks for sharing, and once again this is a Make in India initiative where creating the material in India itself instead of importing it. With that, I will invite Mr. Yatin Huda, Engineers India Limited, to come and start his presentation.
Thank you, Session Chair, for the introduction. Good morning to all the energy professionals present here. After some insightful sessions on AI, 3D printing applications, robotic deburring, and homopolymer polypropylene, I shall be discussing something which is close to every civil engineer's heart, which is concrete the material without which we couldn't have imagined the era of industrialization we are into it. You must be surprised to know that concrete is the second most consumed material on earth after water. So when the extent of utilization of concrete is to such larger values, it is pertinent for us to work upon the carbon reduction methods to make it more sustainable in production. On this stage of manufacturing and industrialization, my topic shall be experimental study of mechanical properties of concrete containing bagasse ash for reducing carbon footprint of construction industry. This specifically lies in the subcategory of zero waste, lean manufacturing and sustainable production methods. This aims to make some transformative sustainable solutions for the manufacturing of cement. The research findings which I have presented here are being worked upon in association with Indian Academy of Sciences during my research project at IIT Bombay. And I shall be correlating it with the EIL projects which we are executing, and will let you know that how EIL is working upon some sustainable solutions at its project's execution sites. We know that concrete is a homogeneous material which is made up of aggregates, cement, water, or some supplementary cementitious materials. By supplementary cementitious materials, I mean apart from cement, which is the binding constituent of concrete, we use certain cementitious material which are at par with cement. We can add them into the concrete making and make it a sustainable concrete technology production method. So my material which I am being using here is sugarcane bagasse ash. These are used in sugar mills. It is the residual material, molasses of the sugarcane, which when dried upon may be used as a fuel, combustion fuel in the sugarcane making itself. And this ashes which remain after the incineration process, we pulverize it to the particle size of a cement, and we may use as a replacement for the cement. So this material can be transformed by incineration and pulverization, and what we can make out of it is ECC, which is engineered cementitious material. So without a further ado, the content of presentation which I am going to present is, I'll be discussing about concrete utilization extent in the mega projects, and the need for the present study, its objectives, methodology followed in the present study, and discussion of result analysis and a way forward. So firstly, discussing about the India's mega construction industry. I was fortunate enough to be part of execution team of two prestigious projects of India. Firstly, the HPCL Rajasthan Refinery project, where I've been associated with DFCU unit, execution of DFCU unit. So you may see the project cost itself is a humongous one, that is 72,937 crores, and concrete, if I talk about, that is 15,76,000 m cubes of concrete. You can imagine a 1 m cube and could relate how much concrete it has been used in this project. Second project in which I am currently working in is 500 KTPA PDHPP Gale-Usar project. It is India's first propane dehydrogenation project, and the project cost is 11,256 crores, and here also the RCC quantity 2,20,000 m cubes. So with such humongous quantities of concrete, we need to look after some sustainable solution for production of concrete. We have set some international net zero targets in COP28 Dubai to make net zero emission of cement production a reality by 2030. The carbon emission itself from the cement industry is estimated to be 177 million metric tons. So it's for India only, and if I talk about world, it's 1.6 billion tons. So India, where approximately 31 to 32% of manufacturing industry we have, cement industry is the major contributor to the carbon emissions. The scale of production, India is the second largest polluter for cement manufacturing across the globe. So we have the obligation to turn it to a sustainable production way. The consumption trends are 450.78 million tons by the end of fiscal year 27. And the growth forecast, if I talk about, which will have a compounded annual growth rate specifically for the cement industry, shall be 4 to 5% over the 4 periods up to fiscal year 27 itself. These are some sustainable cement production methods, cutting the clinker. I won't touch deeply into the how concrete is being made, and I will directly brief you about cement production method. There are basically two methods to make cement. One is the wet method of production, and other one is the dry method. So the clinker, which is the main constituent of cement, it is pulverized, it is fused, and again pulverized to make bogus compounds. These bogus compounds are the compounds which constitute the binding property into the concrete. So the second method is the replacing limestones. Third one is the fuel switching and electrification, rather using the conventional method of heating and pulverizing, and we can use some renewable sources of energy to make clinker fuse and pulverize. Fourth one is the carbon capture. So my present study is SCBA. It shall be focusing on the replacing limestone itself. So the need for the present study: concrete is a composite material, as I have discussed. From 1 kg of cement production, we nearly get about 0.6 to 0.8 kgs of CO2. So you can very well estimate where the cement industry in carbon emissions. The sugarcane bagasse ash obtained from the combustion of sugarcane can be used in partial replacement for cement owing to its pozzolanic nature, which provides strength to cement. SCBA is abundant byproduct of sugar mills, ethanol blending plants, and it is often used as fertilizer, but when dumped into grounds, it clogs the soil and may make the land barren. It is the general case in India that sugar crushers at roadsides dump such SCBA ash, and which makes the land barren itself. It's of no use. So the SCBA composition you can see here, it is very much comparable to the cement composition. It has silica content of 64%, alumina, iron and calcium. Such composition is comparable to cement, and that's why we are using it as a replacement for the cement. Objectives of the study: so we are analyzing flexure and compression strength, whether it is comparable to the normal concrete and sugarcane replaced concrete. The methodology we have followed: this is the design mix and the nomenclature for 5% replacement, for 7.5% replacement of cement, for 10% and 12.5%. The designation are shown for the same. So directly coming to the results, you can see the optimum compressive strength versus SCBA percentage chart, that 7.5 we received the optimal compressive strength for the same, and it is clear that the percentage of SCBA result into increase of compressive strength, but for SCBA specifically, the rate of increase of strength is seen at higher stages. Because it is a pozzolanic material, it takes some time to react completely with water, and that's why the strength received is higher at later stages. Now talking about the flexural, the same trend is seen for the flexure also. At 7.5% we received a maxima, and the addition of fibrous material like SCBA, it has a long fibrous material from the EDS, and which I'll show in coming up slides, which makes the matrix of concrete yield tensile properties. It acts as a small reinforcement in concrete. That's why the flexural strength increases. Next one is the ultrasonic pulse velocity testing. This is basically a non-destructive testing technique. It checks about the homogeneous and density of concrete material. So that too, if it is above 4.4 kilometer per second, that is an excellent category as per our IS standards. And for our case, we received the same at 56 days. owing to the fact that SCBA has a fibrous particle composition. So when water is utilized in intrinsic chemical reactions, the enhanced fibrous property make it dense and thus a homogeneous material. Next one is the scanning electron microscopic method. It was conducted in NITR in Chandigarh only, and from this we can use a focused beam of high energy electrons to generate a variety of signals at the surface of solid specimen, which we have taken from the concrete flexure or concrete compressive strength testing. The signals that derive from electron sample interaction reveals from about the external morphology, texture, and chemical composition, what's inside the concrete, and how it is spread across the surface. Acquiring elemental maps, we can get through this method, and spot chemical analysis we can do. Discrimination of phases based on mean atomic numbers. It can categorize that this is O2, this is oxygen, this is calcium, this is silica. So we can get a spread as demonstrated in the image. Further, the detection limit in EDS depends on sample surface condition. Smoother the surface, lower the detection limits. And EDS can detect major minor element with concentration higher than 10% of the weight. And minor concentration it can also check out with a variation of 1 to 10% in weight. The detection limit for bulk materials, it is 0.1% of weight. Therefore, EDS cannot detect trace elements, but it can show you the composition of the material which has been tested. Now discussing the conclusions. The compressive strength of cubical specimen which was tested for compression, maximum of 1.98% for the 7-day specimen, 20.39% for the 28 days, and 5.59 for the 56 days result. These percentages are comparable, are in comparison to the nominal mix, which is without containing sugarcane bagasse ash. The flexural strength shows the same trend, that is 25.62% for 28 days, 31.92% for 56 days, and results compared to 0% SCB only. Further increase in replacement of cement by SCBA lead to decrease in flexural strength of specimen. The percentage change in strength parameters, increase in flexural strength of specimen is more than the percentage increase in the compressive strength. And this is owing to the fact that it is a fibrous and elongated material. It is as good as a reinforcement itself, but at a smaller scale. The NDT testing, which is UPV test, it was observed that as age of concrete increases, the time duration in the, as you seen in the previous slides, the time duration reduces, indicating that the material we obtained is a dense material, which is good for construction activity. The composition of concrete, it was observed that appropriate proportion of SCH gel. SCH gel is the major constituent of bogus compounds, which is the binding material in the concrete. Now discussing about the future scopes. The stress strain behavior, elastic modulus, freezing thaw resistance of sugarcane bagasse ash as a replacement of cement can be investigated apart from this study. And durability, permeability tests are there, which we can conduct to know that whether the concrete form is not porous. And performance of RCC, which influences sugarcane bagasse ash as replacement of cement on flexural behavior of reinforced concrete beams may be carried out. Because it was not carried out on reinforced cement concrete, it was carried out on a plain cement concrete. We can take up it in the reinforced concrete also. Different grades of concrete can be checked. We made it for M30 grade, that is 30 newtons per mm square is the envisaged strength for the concrete. We can check out for some other grades, M25, M50, or even if for higher grades also, M60. We may conduct it at smaller intervals, like we have taken 2.5 interval of replacement. We may cut down it to 1% to get into more exact results. Lastly, I would like to stress upon the bottom line that the carbon reduction, which take a back step in the innovation era of today. We must focus on the carbon reduction methodologies. In EIL also, at field, we are taking up smaller initiatives like RCA aggregates have been used in concrete at less important structures. Maybe in pavements, we are using demolished concrete aggregates and making designs. So such novel technologies of cement manufacturing industry are also being worked upon by EIL and in discussion to use in such mega projects. Thank you for being so patiently listening to me.
Thank you, Mr. Huda. None of our discussion nowadays can be complete without talking about the carbon footprint. Every organization pledging to have net zero at certain years, and every organizations are working. And I would like to thank Mr. Huda to share his experience of using some material that could never be used or waste material and repurposing the material to improve the carbon footprint in civil industry. Thanks a lot. With that, we are going to conclude the session today. Though there is no Q&A session, however, we can have around 5 minutes time if any of you would like to ask any questions to our esteemed speaker. Though there is an opportunity afterwards to discuss offline also. If any of you have any questions, please. Okay, thank you. Thank you for your presence. Thanks a lot.